In this lesson, you will learn to define independent events using the new mathematical definition, and use the definition of independent events to solve probability problems. Take your notes out from the disjoint events lesson. Please review that lesson again if you need a refresher on the notes suggestion. Recall in that lesson, we suggested that the top half of the notes page should be labeled disjoint events, and to fill out that section with what you learned from that lesson. Now the bottom half should be labeled independent events. That's what we'll fill out today. First, we'll start with defining independence mathematically. Our old definition for two independent events might be two events A and B are independent if A and B do not affect each other. That's not incorrect. That just doesn't have the mathematical context that we want for statistics. So here's our new definition of independence. Two events, A and B, are independent if and only if the probability of A and B equals the probability of A times the probability of B. Or the probability of A given B equals the probability of A. We won't address the second part, which is talking about conditional probabilities in this lesson. We will address that in another lesson. But we will talk about the first one. The probability of A and B equals the probability of A times the probability of B. So what I want you to start thinking about right now is, if I ask you if two events are independent, I don't want you to say, yes, they're independent because they have nothing to do with each other. That's our old definition. I want you to start thinking of our new definition, which is, yes, they're independent because they satisfy this mathematical condition. Or, no, they're not independent because they do not satisfy this mathematical condition. We'll see some examples of this now. Here's an independent example. Let A represent Josephine going to the choir concert, and let B represent Monica going to the choir concert. The probability that both Josephine and Monica go to the choir concert is 0.42. The probability that Josephine goes to the concert is 0.6. And the probability that Monica goes to the concert is 0.7. Why are A and B independent? Well, remember my definition of independence? It's the probability of A and B equals the probability of A times the probability of B. So in this example, does the probability of Josephine and Monica going to the concert equal the probability of Josephine going to the concert times the probability of Monica going to the concert? Let's see. The probability of both going is 0.42. Does that equal 0.6 times 0.7? Yes, it does. Since the probability that both of them going to the concert equals the probability that Josephine goes times the probability that Monica goes, we are in a case where these are independent events. Let's look at our first example. Remember that professor deciding between term papers and watching TV? She's back. The probability that a professor grades term papers on a Friday night is 0.28. The probability that the same professor watches a full season of her favorite TV show on Friday night is 0.32. If grading the term papers and watching a full TV season are independent, find the following probabilities. A, what's the probability of grading the term papers and watching a full TV season? And B, what's the probability of grading the term papers or watching a full TV season. Let's see how this differs from when we talked about this example before when the events were disjoint. Pause the video and try the problem. Let's take a look at the solutions. In part A, I asked you what is the probability of grading and watching TV. Since I told you the events are independent, you can take the probability of grading, which is 0.28, times the probability of watching TV, which is 0.32, and multiply those together to get 0.0896. I can only multiply these together because I told you they are independent. That's something you always want to look for in a problem. You can't just multiply till your heart's content. You have to know the events are independent before you multiply. For part B, I want to know the probability of grading or watching TV. Hopefully the bells are going off in your head to use that formula. I'll write it down in terms of my problem. Probability of G or TV equals a probability of grading plus the probability of TV minus the probability of both. Well, let's take a look at what we know from our problem. We know the probability of grading and we know the probability of watching TV. From part A, we know the probability of both. So I know 0.28 and 0.32 from the problem, and I know 0.0896 from my work in part A. If I do this math, I get the probability of grading or watching TV is 0.5104. Let's try another example. In example 2, 2 fair dice are rolled and the sum is observed. Assume each die has faces 1 through 6. Let A represent an odd sum. Let B represent a sum greater than 8. A. Find the probability of A or B. And B. Are these events independent? Why or why not? Pause the video to try this on your own. Click play when you're ready to continue. As I suggested in the disjoint events lesson, whenever you're talking about the sum of 2 dice, make a chart of possible outcomes. Remember, it looks something like this. To answer part A, option 1 is to just count using our chart. I want to know what's the probability of getting an odd sum or a sum greater than 8. Well, I'll look for all of my odd sums, in other words, all 3s, 5s, 7s, 9s, and 11s. Now I also want all of the sums greater than 8. Well, that's adding in the 10s and the 12s. If I count up all the numbers that I notated, there's 22 of them. Therefore, the probability of getting a sum that is odd or greater than 8 is 22 out of 36. Option 2, to answer this question, is to use our formula. So the formula says the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. The probability of A was 18 out of 36. There were 18 odd sums. The probability of B was 10 out of 36. There were 10 sums greater than 8. Now I need to see which ones satisfy both conditions to find the probability of A and B. If you notice, 9 and 11 are both odd and greater than 8. There are 6 ways to get an odd sum and a sum greater than 8. Therefore, the probability of A and B in this situation is 6 out of 36. If I do this math, I get the answer 22 out of 36. Notice, I could have used option 1 or option 2. Either gives me the same answer. Now, to answer part B, are the events independent? If two events are independent, then the probability of A and B would equal the probability of A times the probability of B. In this situation, that means the probability of an odd sum and a sum greater than 8 should be equal to the probability of an odd sum times the probability of a sum greater than 8, if they were independent. So, does 6 out of 36 equal 18 out of 36 times 10 out of 36? Cleaning this up a bit, does 6 over 36 equal 5 over 36? No. Therefore, the events are not independent. How I want you to write this is, since the probability of A and B does not equal the probability of A times the probability of B, the events are not independent. Of course, I want you to show the work that you see in front of you, actually plugging in the numbers so that we can see that the probabilities do not equate. Now, let's test what you've learned so far with a check for understanding. A fair die is rolled. Let A represent an even number being rolled, and let B represent a prime number being rolled. A, are A and B disjoint? Why or why not? And B, are A and B independent? Why or why not? See if you can answer this without looking at your note sheet. If you need to, that's fine, but know that you'll need more practice later on. Pause the video to work on this. Click play when you're ready to resume. In event A, the die showed an even number when it was rolled. In event B, the die showed a prime number when it was rolled. So I would suggest you do is write out the sample outcomes for this event. For A, even numbers would be 2, 4, or 6. For B, a prime number would be 2, 3, or 5. I know some of us might have needed a refresher on prime numbers. So by definition, 1 is not a prime number. So 2, 3, and 5 are the numbers on a die that are prime. So are these events disjoint? Do the sample spaces have something in common? Yes, they do. A and B are not disjoint since they have a common outcome. That outcome is 2. Therefore, they can occur at the same time, so the events are not disjoint. The other way you could have written this is that the probability of A and B does not equal 0. In part B, are the events independent? If the events were independent, then we know the probability of A and B equals the probability of A times the probability of B. Well, the probability of A is 3 out of 6. The probability of B is also 3 out of 6. And the probability of A and B is 1 out of 6. Remember, that's a probability of rolling a 2. So there's only one way out of 6 to roll a 2. Let's substitute these probabilities to see if it satisfies our independent condition. Does 1/6 equal 3/6 times 3/6? No, it does not. Since the probability of A and B does not equal the probability of A times the probability of B, the events are not independent. As you're looking at what you wrote in comparison to what I have here, Make sure that you have a logical sequence to tell me whether the events are independent or not. I always start with a statement. If they were independent, then this would be true. Then you'll show me whether it is or isn't true to make the then statement. If it is true, then the events are independent. If it isn't true, then the events are not independent. And that's the case that we have here. Now it's time for the wrap-up. After this lesson, you should be able to define independent events using the new mathematical definition, and use the definition of independent events to solve probability problems. This concludes this lesson on independent events. Remember, you can review this video as many times as needed for better understanding. Thanks for watching.